Hello everyone, thanks for coming back, or if this is your first time here, welcome. This is Learn While You Sleep or Relax. I originally created this channel to help me sleep. I got tired of falling asleep to videos full of nonsense, fake history, and made-up facts. I wanted something calm, factual, and trustworthy. Real history, real science, real information. So if you're here to unwind, rest, or fall asleep, you're in the right place. This channel is all about helping you learn real facts while you sleep and relax. If you appreciate the effort that goes into these videos, likes and subscribes are always very appreciated. It really does help the channel grow. Feel free to leave a comment letting me know what time it is, where you are, and where you're watching from. I love seeing how far these videos reach. Now get comfortable, settle in, relax, and let's begin. Today we are going to learn about rock geology. In geology, a rock or stone is any naturally occurring solid mass or aggregate of minerals or mineraloid matter. Rocks are categorized by their mineral content, chemical composition, and formation process. They constitute the Earth's outer solid layer, the crust, and much of its interior, excluding the liquid outer core and areas of magma in the asthenosphere. The study of rocks encompasses various subdisciplines, including petrology and mineralogy, and may focus on Earth-specific rocks or extend to planetary geology, which examines the rocks of other celestial bodies. Rocks are classified into three primary types: igneous, sedimentary, and metamorphic. Igneous rocks form when magma cools within the Earth's crust, or when lava cools on the surface or seabed. Sedimentary rocks arise from diagenesis and lithification of sediments that are created through the weathering, transport, and deposition of existing rocks. Metamorphic rocks develop when existing rocks experience high pressures and temperatures, causing transformation without significant melting. Humanity has utilized rocks since the time of early human beings. This era, known as the Stone Age, marked the creation of many stone tools. Stone became a crucial material in constructing buildings and early infrastructure. Mining emerged to extract rocks from the earth and access the minerals they contain, including metals. Today, modern technology has enabled the creation of new human-made rocks and rock-like materials, such as concrete. Geology is the study of Earth and its components, including rock formations. Petrology examines the character and origin of rocks, while mineralogy focuses on the mineral components that make up rocks. This study has enhanced our understanding of Earth's history, human history, and the advancement of engineering and technology. Though various theories about rocks have existed throughout history, geology emerged as a formal science in the 19th century. During this time, Plutonism was introduced as a theory. The discovery of radioactive decay in 1896 enabled radiometric dating of rocks. In the latter half of the 20th century, knowledge of plate tectonics also developed. Rocks are composed primarily of grains of minerals, which are crystalline solids formed from atoms that are chemically bonded in an orderly structure. Some rocks also contain mineraloids, rigid substances like volcanic glass that lack a crystalline structure. The types and amounts of minerals in a rock depend on how it was formed. Most rocks contain silicate minerals, compounds with silica tetrahedra in their crystal lattice. Silicate minerals account for about 1/3 of all known mineral species and about 95% of the Earth's crust. The proportion of silica in rocks and minerals is crucial in determining their names and properties. Rocks are classified based on characteristics such as mineral and chemical composition, permeability, texture, and particle size. These physical properties arise from the processes involved in their formation. Over time, rocks can transform from one type to another, a process described by the rock cycle. This transformation leads to three general classes of rock: igneous, sedimentary, and metamorphic. These classes are further divided into various groups. However, there are no strict boundaries between related rocks. By increasing or decreasing the proportions of minerals, rocks transition gradually from one type to another. The distinctive structures of one rock type can merge into those of another, meaning that the definitions used in rock classification represent selected points in a continuous spectrum. Igneous rock, derived from the Latin word for fire, is formed through the cooling and solidification of magma or lava. This magma may come from partial melts of pre-existing rocks in a planet's mantle or crust. The melting of rocks typically results from one or more of three processes: an increase in temperature, a decrease in pressure, or a change in composition. Igneous rocks are divided into two main categories. Plutonic or intrusive rocks form when magma cools and crystallizes slowly within the Earth's crust. A common example of this type is granite. Volcanic or extrusive rocks result when magma reaches the surface as lava or fragmental ejecta, creating minerals such as pumice or basalt. As magmas rise towards the Earth's surface, they tend to become richer in silica, a process known as magma differentiation. This occurs because minerals low in silica crystallize out of the magma as it cools, and because the magma assimilates some of the crustal rock through which it ascends. Crustal rock is typically high in silica. Consequently, silica content is the most important chemical criterion for classifying igneous rock, with alkali metal oxides following closely in significance. Approximately 65% of the Earth's crust by volume consists of igneous rocks. Of these, 66% are basalt and gabbro, 16% are granite, and 17% are granodiorite and diorite. Only 0.6% are syenite, and 0.3% are ultramafic. The oceanic crust is mainly basalt, which is an igneous rock of mafic composition. Granite and similar rocks, known as granitoids, dominate the continental crust. Sedimentary rocks are formed at the Earth's surface through the accumulation and cementation of fragments from earlier rocks, minerals, and organisms, or as chemical precipitates in organic growth in water. This process leads to the settling and accumulation of clastic sediments, which are fragments of rock and organic particles. Minerals may also chemically precipitate from a solution. Before deposition, sediments are created by the weathering of earlier rocks through erosion in a source area. They are then transported to deposition sites by water, wind, ice, mass movement, or glaciers. Sedimentary rocks make up about 7.9% of the Earth's crust by volume. Of these, 82% are shales, with 6% being limestone and 12% sandstone and arkoses. These rocks often contain fossils. Sedimentary rocks typically form under the influence of gravity, resulting in horizontal or nearly horizontal layers, known as strata. They can be referred to as stratified rocks. The particles in clastic sedimentary rocks can be classified by grain size, ranging from the smallest, clay, to silt, sand, and gravel, with some systems also including cobbles and boulders. Metamorphic rocks are formed by subjecting any rock type, sedimentary, igneous, or another metamorphic rock, to different temperature and pressure conditions than those in which the original rock was created. This process, known as metamorphism, leads to significant changes in the rock's physical properties and chemistry. The original rock, called the protolith, can transform into new mineral types or different forms of the same minerals through recrystallization. Such transformations require conditions that are always more extreme than those at the Earth's surface, with temperatures above 150 to 200 degrees Celsius and pressures exceeding 1500 bars. This process commonly occurs when continental plates collide. Metamorphic rocks make up 27.4% of the Earth's crust by volume. There are three major classes of metamorphic rock based on their formation mechanisms. Contact metamorphism occurs when magma intrudes and heats the surrounding rock, resulting in a temperature-dominant transformation. Pressure metamorphism, or burial metamorphism, happens when sediments are buried deeply, where pressure is predominant over temperature. This can lead to the formation of rocks such as jade. Regional metamorphism, where both heat and pressure influence the rock, is generally found in mountain-building regions. Metamorphic rocks can be divided into two general categories based on their structure. Those with a textured appearance are called foliated, while those without such a texture are non-foliated. The classification of the rock is based on the types of minerals present. Schists are foliated rocks that primarily consist of lamellar minerals, especially micas. Gneiss features visible bands of differing lightness, with granite gneiss being a common example. Other foliated varieties include slates, phyllites, and myelinite. Well-known non-foliated metamorphic rocks include marble, soapstone, and serpentine. This category also contains quartzite, which is a metamorphosed form of sandstone, and hornfels. Extraterrestrial rocks. Though most understanding of rocks comes from those on Earth, rocks also make up many celestial bodies in the universe. In the solar system, Mars, Venus, and Mercury are composed of rock, along with many natural satellites, asteroids, and meteoroids. Meteorites that fall to Earth give insight into the composition of these extraterrestrial rocks. They are typically heavier than those found on Earth. Additionally, asteroid rocks can be collected and brought back through space missions, such as the Hayabusa mission. Lunar rocks and Martian rocks have also been the subject of study. Human use of rock has significantly influenced cultural and technological development. For at least 2.5 million years, rock has been utilized by humans and other hominids. Lithic technology represents one of the earliest and most enduring forms of technology. The mining of rock for its metal content has been crucial for human advancement. This process has evolved at varying rates across different regions, influenced by the types of metals available in local rock. Anthropic rock is synthetic or restructured rock formed by human activity. Concrete is a well-known example, created from natural and processed materials, with its use dating back to ancient Rome. Other forms of rock can also be modified using various substances, such as epoxy granite. Additionally, artificial stones like codestone have been developed. Geologist James R. Underwood has proposed that anthropic rock should be considered a fourth class of rocks, alongside igneous, sedimentary, and metamorphic. Building. Rock varies greatly in strength. Quartzites can have a tensile strength exceeding 300 megapascals, while some sedimentary rocks are so soft that they can be crumbled with bare fingers. For context, structural steel has a tensile strength of around 350 megapascals. Sedimentary rock, which is relatively soft and easy to work with, was quarried for construction as early as 4000 BCE in Egypt. Additionally, stone was used to build fortifications in Inner Mongolia around 2800 BCE. Tuff, a soft rock common in Italy, was extensively used by the Romans for buildings and bridges. In the Middle Ages, limestone became widely used in construction across Europe and maintained its popularity into the 20th century. Mining is the extraction of valuable minerals or other geological materials from the earth, often from an ore body, vein, or seam. This process also includes the removal of soil. Materials recovered through mining encompass base metals, precious metals, iron, uranium, coal, diamonds, limestone, oil shale, rock salt, potash, construction aggregate, and dimension stone. Mining is essential for obtaining resources that cannot be grown through agriculture or created artificially. Mining has been practiced since prehistoric times. Modern methods involve several steps: prospecting for mineral deposits, analyzing the potential profitability of a mine, extracting the desired materials, and reclaiming the land for future use after mining ends. However, mining can have negative environmental impacts, both during operations and for years thereafter. These consequences have led many countries to adopt regulations aimed at managing the adverse effects of mining activities. Tools. Stone tools have been used for millions of years by humans and earlier hominids. The Stone Age marked a significant period of widespread stone tool usage. Early Stone Age tools were simple, including hammerstones and sharp flakes. Middle Stone Age tools introduced sharpened points, which served as projectile points, awls, or scrapers. During the Late Stone Age, tools evolved with greater craftsmanship and distinct cultural identities. Eventually, stone tools were largely replaced by copper and bronze tools with the advent of metallurgy. Geology is a branch of natural science focused on the Earth, other astronomical bodies, and the rocks they comprise, as well as the processes that cause changes over time. The term originates from the ancient Greek words for earth and study of. Modern geology intersects with various earth sciences, including hydrology, and is integrated with earth system science and planetary science. It examines the structure of the Earth both on the surface and beneath, exploring the processes that have shaped this structure. Geologists analyze the mineral composition of rocks to gain insights into their formation history. Geology establishes the relative ages of rocks in a specific area, while geochemistry, a subfield of geology, determines their absolute ages. By employing petrological, crystallographic, and paleontological tools, geologists can chart the geological history of the Earth. This includes efforts to establish the Earth's age and provide evidence for plate tectonics, evolutionary history, and the planet's past climates. Geologists study the properties and processes of Earth and other terrestrial planets through a range of methods such as fieldwork, rock descriptions, geophysical techniques, chemical analyses, physical experiments, and numerical modeling. Geology plays a crucial role in mineral and hydrocarbon exploration, assessing water resources, understanding natural hazards, addressing environmental issues, and offering perspectives on past climate changes. As a major academic discipline, geology is vital to geological engineering and has a significant impact on geotechnical engineering. Geological material encompasses the solid Earth materials that provide essential data for understanding our planet. Most of this information is derived from research focused on these materials. Additionally, meteorites and other extraterrestrial substances are examined through geological methods, expanding our knowledge beyond Earth. Minerals are naturally occurring elements and compounds with a definite homogeneous chemical composition and an ordered atomic arrangement. Some amorphous substances that resemble minerals are called mineraloids, although there are exceptions such as georgite and autunite. Amorphous substances formed by geological processes may be considered minerals if their original form was a mineral before metamictization. Each mineral has distinct physical properties, and various tests can determine these. Minerals are often identified through color. Minerals are categorized by their color, which can be diagnostic, though impurities may alter a mineral's appearance. Streak. This test involves scratching the sample on a porcelain plate to observe the color of the resulting streak, aiding in identification. Hardness. This measures a mineral's resistance to scratching or indentation. Breakage pattern. Minerals exhibit either fracture or cleavage. Fracture results in uneven surfaces, while cleavage occurs along closely spaced parallel planes. Luster. This describes how light reflects off a mineral's surface, with categories including metallic, pearly, waxy, and dull. Specific gravity. This refers to the weight of a specific volume of a mineral. Effervescence. This test involves applying hydrochloric acid to the mineral to check for fizzing. Magnetism. A magnet test is used to assess a mineral's magnetic properties. Taste. Some minerals, like halite, can be identified by their distinct taste, resembling table salt. A rock is any naturally occurring solid mass or aggregate of minerals or mineraloids. Research in geology primarily focuses on rocks as they record much of the Earth's geological history. There are three major types of rock: igneous, sedimentary, and metamorphic. The rock cycle illustrates the relationships among these types. Igneous rocks form when molten rock, known as magma or lava, solidifies or crystallizes. The active movement of this molten rock is studied in volcanology, and igneous petrology examines the history of igneous rocks from their origin to their final crystallization. Rocks can undergo weathering and erosion before being redeposited and lithified into sedimentary rocks. These rocks are mainly divided into four categories: sandstone, shale, carbonate, and evaporite. This classification considers both sediment particle size, as seen in sandstone and shale, and mineralogy and formation processes, like carbonation and evaporation. Igneous and sedimentary rocks can also transform into metamorphic rocks through heat and pressure, altering their mineral content and giving them a distinct fabric. All three types may melt again, producing new magma, which can solidify into igneous rock once more. Organic matter, including coal, bitumen, oil, and natural gas, is primarily associated with organic-rich sedimentary rocks. To study all three rock types, geologists analyze their minerals and physical properties, such as texture and fabric. Geologists study unlithified materials, also known as superficial deposits, which are found above the bedrock. This area of research is often referred to as quaternary geology, named after the Quaternary period, the most recent period in geologic history. Plate tectonics describes the Earth's lithosphere, which includes the crust and the rigid uppermost part of the upper mantle. In the 1960s, it was discovered that this lithosphere is divided into tectonic plates that move across the plastically deforming upper mantle, known as the asthenosphere. This movement is supported by various observations, including seafloor spreading and the global distribution of mountains and earthquakes. The movement of these plates is closely linked to the convection of the mantle, which involves heat transfer due to the slow movement of ductile mantle rock. Oceanic parts of the tectonic plates and the underlying mantle convection currents move in the same direction. This relationship forms the basis of the theory of plate tectonics. The theory has provided a framework for understanding numerous geological phenomena. Long linear geological features correspond to plate boundaries. Mid-ocean ridges are seen as divergent boundaries, where two plates move apart, creating high areas on the seafloor with hydrothermal vents and volcanoes. Arcs of volcanoes and areas of seismic activity are associated with convergent boundaries, where one plate subducts beneath another. Transform boundaries, such as the San Andreas Fault System, occur where plates slide horizontally past each other. Plate tectonics also supports Alfred Wegener's theory of continental drift, explaining how continents shift over geological time. It offers a mechanism for crustal deformation and a context for structural geology observations. The strength of plate tectonics lies in its ability to unify these geological observations into one comprehensive theory of lithospheric movement above the convecting mantle. Advances in seismology, computer modeling, and mineralogy, along with crystallography under high temperatures and pressures, provide valuable insights into the Earth's internal composition and structure. Seismologists utilize the arrival times of seismic waves to investigate the Earth's interior. Early breakthroughs revealed a liquid outer core, indicated by the absence of shear wave propagation and a dense, solid inner core. This understanding led to a layered model of the Earth, which includes the lithosphere, comprising the crust above the mantle. The mantle is further divided by seismic discontinuities at depths of 410 and 660 kilometers, with the outer and inner cores lying beneath. Since the 1970s, innovations such as seismic full waveform inversion have enabled scientists to create detailed images of wave speeds within the Earth. This technique is akin to using a CT scan to visualize a body, resulting in a more sophisticated view of the Earth's interior that replaces the earlier simplified model with a more dynamic one. Mineralogists have leveraged the pressure and temperature data from seismic studies alongside the elemental composition of the Earth to recreate these conditions in laboratory settings. This approach allows for measuring changes within crystal structures, explaining the chemical transformations associated with the major seismic discontinuities in the mantle and revealing the expected crystallographic structures of the Earth's inner core. The geological timescale encompasses the history of the Earth. It begins with the first solar system material at 4.567 billion years ago, and the formation of the Earth at 454 billion years ago, marking the start of the Hadean Eon. The scale extends to the present day, currently within the Holocene epoch. The timescale of the Earth is represented in 5 timelines. The first timeline illustrates the entire span from Earth's formation to the present, but does not allow for much detail on the most recent eon. The second timeline provides an expanded view of this eon. The third timeline focuses on the most recent era, while the fourth timeline zooms in on the latest period. Finally, the fifth timeline expands on the most recent epoch. 4.567 billion years ago marks the formation of the solar system. 454 million years later, Earth itself began to form. Around 450 million years ago, a significant impact is proposed to have formed the Moon. Approximately 4 billion years ago, the late heavy bombardment ended and the first life emerged. By 3.5 billion years ago, photosynthesis began. Between 3.2 and 2.3 billion years ago, the Earth's crust transitioned from a stagnant lid to plate tectonics. Around 2.3 billion years ago, the atmosphere became oxygenated, leading to the first snowball Earth event. Between 1.8 and 1.5 billion years ago, the Columbia supercontinent existed, followed by Rodinia from 1,100 to 750 million years ago. The second snowball Earth event occurred between 730 and 635 million years ago. The Pannotia supercontinent formed between 650 and 540 million years ago, with the Cambrian explosion occurring around 541 million years ago. This period saw a vast multiplication of hard-bodied life, the first abundant fossils, and the beginning of the Paleozoic era. Around 380 million years ago, the first vertebrate land animals appeared. The supercontinent Pangaea existed from 300 million to 180 million years ago. The Permian-Triassic extinction, which eliminated 90% of all land animals, occurred 250 million years ago, marking the end of the Paleozoic and the beginning of the Mesozoic era. 66 million years ago, the Cretaceous-Paleogene extinction event led to the demise of the dinosaurs, signaling the end of the Mesozoic and the beginning of the Cenozoic era. Between 45 and 35 million years ago, the Himalayas mountain range began to form. Around 7 million years ago, the first hominins appeared, followed by the emergence of the first Australopithecus, a direct ancestor of modern Homo sapiens, approximately 3.9 million years ago. Finally, around 200,000 years ago, the first modern Homo sapiens appeared in East Africa. The epochs of lunar history are based on the chronology of impact events named after significant impacts. The Imbrian epoch, for example, is named after the formation of the Mare Imbrium basin. The ages of older lunar basins can be determined by assessing the strength of their intrinsic magnetic fields. The early moon had a magnetic field that diminished over time. Additionally, the ages of craters can be estimated through morphological and stratigraphic classifications, with younger craters overlapping older impacts and typically displaying less wear from impacts. Epochs on Mars are divided into several distinct periods based on geological features and ages. The Noachian epoch represents the earliest period, characterized by a heavily cratered surface, indicating a time of significant impact events. It lasted from approximately 4.6 billion to 3.5 billion years ago. The Hesperian epoch follows, marked by volcanic activity and the presence of extensive lava flows. This period spans from around 3.5 billion to 3 billion years ago. Finally, the Amazonian epoch is the most recent, lasting from about 3 billion years ago to the present. During this time, Mars experienced a decline in volcanic activity and features indicating the potential for past water activity. Each epoch reflects a unique chapter in the geological history of Mars, revealing a planet that has undergone significant changes over billions of years. Relative dating methods were established as geology emerged as a natural science. Geologists still apply these principles to understand geological history and the timing of events. The principle of uniformitarianism asserts that the geological processes we observe today have operated similarly throughout geological time. This concept, advanced by 18th century Scottish physician and geologist James Hutton, suggests that the present is the key to the past. Hutton emphasized that the Earth's history should be explained by current observable processes. The principle of intrusive relationships involves cross-cutting intrusions. When an igneous intrusion cuts across a sedimentary rock formation, it indicates that the igneous intrusion is younger than the sedimentary rock. Types of intrusions include stocks, laccoliths, batholiths, sills, and dikes. The principle of cross-cutting relationships concerns faults and the age of the rock sequences they cut through. Faults are younger than the rocks they disrupt. If a fault intersects certain formations but not others above it, the disrupted formations are older than the fault, while those not intersected are younger. Identifying the key bed in these scenarios can help differentiate between normal and thrust faults. The principle of inclusions and components states that inclusions, or clasts, found in sedimentary rock must be older than the rock containing them. For instance, gravel from an older layer may be incorporated into a newer layer. A similar instance occurs in igneous rocks with xenoliths, which are foreign materials that get carried into magma or lava flows and later solidify within the surrounding rock, indicating they are older than the rock they are found in. The principle of original horizontality explains that sediments are typically deposited in horizontal layers. This is supported by observations of modern marine and non-marine sediments across various environments, even though some layers may be inclined. The principle of superposition indicates that in an undisturbed sequence of sedimentary rocks, a layer is younger than the one beneath it and older than the one above it. Essentially, a younger layer cannot slip beneath a previously deposited layer. This principle allows sedimentary layers to represent a vertical timeline, recording the time from the deposition of the lowest layer to the highest. The principle of faunal succession is based on the distribution of fossils in sedimentary rocks. Since organisms existed concurrently across the globe, their presence or absence in formations provides a relative age. This principle, outlined by William Smith nearly a century before Darwin's theory of evolution, developed independently of evolutionary ideas. However, it becomes complex due to uncertainties in fossilization, variations in fossil types due to habitat changes, and differences in global fossilization timelines. Geologists use methods to determine the absolute age of rock samples and geological events. These methods may be used alongside relative dating techniques to enhance accuracy. At the start of the 20th century, advancements in geological science were propelled by the ability to obtain precise absolute dates using radioactive isotopes and other methods. This innovation transformed the understanding of geological time. Previously, geologists relied on fossils and stratigraphic correlation for relative dating. With the introduction of isotopic dates, it became possible to assign absolute ages to rock units, which in turn allowed for the conversion of relative ages into absolute ages for fossil sequences that contained datable material. In many geological applications, isotope ratios of radioactive elements are measured in minerals to determine how much time has elapsed since a rock reached its closure temperature, the point where radiometric isotopes cease to diffuse in and out of the crystal lattice. This is significant for both geochronologic and thermochronologic studies. The most suitable isotopic systems for this purpose include uranium-lead, rubidium-strontium, and potassium-argon. Uranium-thorium dating specifically applies to calcium carbonate materials. Dating lava and volcanic ash layers within a stratigraphic sequence can yield absolute age data for sedimentary rock units lacking radioactive isotopes, and can also calibrate relative dating methods. These techniques help determine the ages of Pluton emplacement. The fractionation of lanthanide series elements is used to compute ages from rocks removed from the mantle. For more recent geological events, optically stimulated luminescence and cosmogenic radionuclide dating are employed to date surfaces and erosion rates. Dendrochronology aids in dating landscapes, while radiocarbon dating applies to geologically young materials with organic carbon. Thermochemical techniques are available to determine temperature profiles within the crust, estimate the uplift of mountain ranges, and reconstruct paleotopography. The geology of an area changes over time as rock units are deposited, inserted, and altered by deformational processes. Rock units are first emplaced through deposition onto the surface or intrusion into overlying rock. Deposition occurs when sediments settle and lithify into sedimentary rock, or when volcanic materials like ash or lava flows cover the surface. Igneous intrusions, including batholiths, laccoliths, dikes, and sills, push upwards and crystallize as they penetrate the rock above. Following the initial deposition, rock units can experience deformation and metamorphism. Deformation typically results from horizontal shortening, horizontal extension, or side-to-side motion, which relate to convergent, divergent, and transform boundaries among tectonic plates. Under horizontal compression, rock units shorten and thicken. This occurs mainly through faulting and folding. In the shallow crust, brittle deformation leads to thrust faults, where deeper, often older rock moves atop shallower rock, resulting in older rocks over younger ones. Fault movement can create folds, especially if the faults are not planar. Deeper within the earth, rocks tend to behave plastically, and instead of faulting, they fold. These folds can be classified into antiforms, where the center buckles upwards, and synforms, where it buckles downwards. Anticlines and synclines describe forms where the tops of the folds point upward. If some units face downward, they may be termed overturned anticlines, or synclines. When the orientation of all units is uncertain, they are referred to simply as antiforms and synforms. In regions of higher pressure and temperature, folding can lead to metamorphism, changing mineral compositions, and creating foliation, a planar surface associated with stress. This process often obscures original textures in the rocks. Extension makes rock units longer and thinner, mainly through normal faulting and ductile stretching. Normal faults drop higher rock units beneath lower ones, typically resulting in younger units positioned below older ones. Stretching can narrow units, producing shapes known as boudins due to their resemblance to sausages. Strike-slip faults emerge where rock units slide past each other in shallow regions, transitioning to shear zones at greater depths where ductile deformation occurs. New rock units are often added during deformation, both through deposition and intrusive processes. Faulting creates topographic gradients, leading to erosion on rising rock units, with sediments depositing onto those that descend. Ongoing fault motion sustains these gradients and creates space for further sediment deposit. Deformational events commonly accompany volcanism and igneous activity, with volcanic ash and lava accumulating on surfaces and igneous intrusions emerging from below. Dikes, which are planar igneous intrusions, form along cracks and can appear in swarms, particularly in actively deformed regions. These geological processes do not occur in a singular environment or order. The Hawaiian Islands are predominantly layered basaltic lava flows, while sedimentary sequences in the mid-continental United States and the Grand Canyon retain nearly undeformed layers since the Cambrian period. In contrast, the southwestern United States features a complex mix of sedimentary, volcanic, and intrusive rocks that have undergone metamorphism, faulting, foliating, and folding. Even older formations, such as the Acasta gneiss in northwestern Canada, have experienced such extensive metamorphism that their original compositions are now recognizable only through laboratory analysis. Geological processes can unfold in stages. In some areas, like the Grand Canyon, lower rock units are metamorphosed and deformed before deposition of the upper, undeformed layers. While various rock emplacement and deformation events may occur repeatedly, these ideas help guide our understanding of the geological history of an area. Geologists use a variety of methods to explore Earth's history and processes. They rely on field studies, laboratory analysis, and numerical modeling. Typically, investigations involve petrology, which focuses on rocks, stratigraphy, the analysis of sedimentary layers, and structural geology, the examination of rock positions and deformation. Geologists also study modern soils, rivers, landscapes, and glaciers. They investigate past and current life along with biogeochemical pathways. Additionally, they employ geophysical methods to explore subsurface structures. Within geology, subspecialties may differentiate between endogenous or internal processes and exogenous or external factors. Field methods in geology vary based on the specific objectives. Common fieldwork activities include geological mapping. Structural mapping involves identifying the locations of major rock units, along with the faults and folds associated with their formation. Stratigraphic mapping focuses on locating sedimentary facies, which include lithofacies and biofacies, or creating maps of isopachs, showing areas of equal sedimentary rock thickness. Superficial mapping records the locations of soils and other surface deposits. Surveying topographic features and compiling topographic maps are also essential. Fieldwork aims to understand changes across landscapes, encompassing patterns of erosion and deposition, river channel changes through migration and avulsion, and hill slope processes. Subsurface mapping is conducted using geophysical methods such as shallow seismic surveys, ground-penetrating radar, aeromagnetic surveys, and electrical resistivity tomography. These techniques support hydrocarbon exploration, groundwater discovery, locating buried archaeological artifacts, and providing high-resolution stratigraphy. Measuring and describing stratigraphic sections at the surface, along with well drilling and logging, are also part of this work. Biogeochemistry and geomicrobiology involve collecting samples to determine biochemical pathways, identify new species, and discover new chemical compounds. These findings can help understand early life on Earth and its metabolic processes and lead to important pharmaceutical compounds. Paleontology focuses on the excavation of fossil material for research on past life and evolution, contributing to museums and education. The collection of samples is also integral for geochronology and thermochronology. In glaciology, fieldwork measures the characteristics and motion of glaciers. Petrology is the branch of geology focused on the study and identification of rocks. Petrologists identify rock samples in the laboratory after fieldwork, using methods like optical microscopy and electron microprobe analysis. In optical mineralogy, thin sections of rock samples are examined under a petrographic microscope. Here, minerals are identified based on their properties, including birefringence, pleochroism, twinning, and interference effects when viewed under different types of light. The electron microprobe allows for detailed analysis of individual locations within a rock, revealing their precise chemical compositions and variations within individual crystals. Studies of stable and radioactive isotopes offer additional insights into the geochemical evolution of rock units. To further understand the conditions under which minerals form, petrologists analyze fluid inclusion data and conduct high temperature and pressure experiments. This research details how mineral phases appear and transform during igneous and metamorphic processes. Such studies not only enhance understanding of these processes, but also provide valuable context for geological phenomena like subduction and the evolution of magma chambers. Structural geology involves the study of the arrangement and deformation of rock layers. Structural geologists examine geological samples using microscopic analysis of oriented, thin sections, providing insight into the fabric and strain within rocks. They gather and analyze measurements of geological structures to understand the orientations of faults and folds, reconstructing the history of rock deformation in a given area. Additionally, they conduct both analog and numerical experiments to simulate rock deformation in various contexts. The analysis of structures often involves plotting features' orientations on stereonets. A stereonet represents a stereographic projection of a sphere on a plane, where planes appear as lines and lines as points. This method helps identify locations of fold axes and relationships between faults and other geological structures. Notable experiments in structural geology include those focused on orogenic wedges, which form in regions where mountains develop along convergent tectonic plate boundaries. In analog experiments, horizontal layers of sand are drawn along a lower surface toward a backstop, creating realistic patterns of faulting and the formation of critically tapered orogenic wedges. Numerical models, which are typically more complex, can incorporate effects of erosion and uplift in mountain ranges, revealing how these processes influence the shape of such formations. These studies provide valuable insights into the pathways of metamorphism influenced by pressure, temperature, space, and time. Stratigraphy involves analyzing samples collected from the field, such as drill cores. Stratigraphers study data from geophysical surveys to identify the locations of stratigraphic units beneath the surface. By combining geophysical data and well logs, they gain a clearer picture of the subsurface, often utilizing computer software for three-dimensional modeling. This information allows stratigraphers to reconstruct ancient processes, interpret past environments, and identify potential resources like water, coal, and hydrocarbons. Biostratigraphers focus on rock samples from outcrops and drill cores, examining fossils to date the samples and understand the depositional environments of the rock units. Geochronologists provide more precise dating of the rocks within the stratigraphic section, offering clearer timelines for deposition. Magnetic stratigraphers search for evidence of magnetic reversals in igneous rock units from drill cores. Additionally, some scientists conduct stable isotope studies on rocks to gather insights about past climate conditions. Planetary geology emerged with space exploration in the 20th century, allowing geologists to examine other planetary bodies using the principles developed for Earth. This field, also known as astrogeology, is a key part of planetary science. It primarily focuses on terrestrial planets, icy moons, asteroids, comets, and meteorites, though some planetary geophysicists also study giant planets and exoplanets. The term geology typically includes references to other planetary bodies, as seen in phrases like the geology of Mars or lunar geology. Specialized terms exist as well, such as selenology for the Moon, areology for Mars, and hermesology for Mercury. While planetary geologists explore all features of other planets, a significant emphasis is placed on searching for signs of past or present life. This pursuit has inspired numerous missions aimed at gathering evidence of life on different worlds. An example is the Phoenix lander, which focused on analyzing Martian polar soil for water and chemical and mineralogical constituents related to biological processes. Economic geology is a branch of geology that focuses on the economic minerals essential for meeting human needs. These minerals are extracted profitably for practical applications. Economic geologists play a vital role in locating and managing the Earth's natural resources, including petroleum and coal, alongside various mineral resources such as iron, copper, and uranium. Mining geology consists of the extraction of mineral and ore resources from the Earth. Some resources of economic interest include gemstones, metals like gold and copper, and various industrial minerals such as asbestos, magnesite, perlite, mica, phosphates, zeolites, clay, silica, and pumice. Additionally, elements such as sulfur and helium are also significant. Petroleum geology involves the study of subsurface locations that may contain extractable hydrocarbons, particularly petroleum and natural gas. Since many reservoirs are situated in sedimentary basins, petroleum geologists examine the formation of these basins, along with their sedimentary and tectonic evolution, as well as the current positions of the rock units. Engineering geology is the application of geological principles to engineering practice. Its goal is to address the geological factors that influence the location, design, construction, operation, and maintenance of engineering works. This field is distinct from geological engineering, especially in North America. In civil engineering, geological principles and analyses help determine the mechanical characteristics of the materials used for constructing structures. This knowledge ensures the safe construction of tunnels, supports sturdy foundations for bridges and skyscrapers, and prevents buildings from settling in unstable clay and mud. Hydrology involves the application of geological principles to various environmental challenges. This includes stream restoration, the revival of brownfields, and understanding how natural habitats interact with the geological environment. Groundwater hydrology, or hydrogeology, focuses on locating groundwater, which is often a vital source of uncontaminated water, particularly in arid regions. It also involves monitoring the spread of contaminants in groundwater wells. Paleoclimatology geologists obtain data through stratigraphy, boreholes, core samples, and ice cores. Ice cores and sediment cores are used for paleoclimate reconstructions, providing insights into past and present temperature, precipitation, and sea level across the globe. These datasets serve as the primary source of information on global climate change beyond instrumental data. Natural hazards are a focus for geologists and geophysicists. Their work helps to establish safe building codes and warning systems aimed at minimizing loss of property and life. Key natural hazards related to geology include the study of the physical material of the Earth dates back at least to ancient Greece, when Theophrastus wrote on stones. During the Roman period, Pliny the Elder discussed various minerals and metals in use, accurately identifying the origin of amber. Aristotle, in the 4th century BCE, made critical observations about the slow rate of geological change, suggesting that such transformations occur gradually and are not observable within a single lifetime. He developed one of the first evidence-based theories regarding the Earth's physical changes. Abu al-Rayhan al-Biruni, an early Persian geologist, wrote about the geology of India, proposing that the subcontinent was once submerged under a sea. Ibn Sina, also known as Avicenna, drew from surviving Greek and Indian texts to explain the formation of mountains and the origin of earthquakes, laying a foundational framework for modern geology. In China, Shen Kuo developed a hypothesis on land formation through the study of fossilized shells found high in the mountains, concluding that erosion and sedimentation were responsible for the creation of land. Georgius Agricola is regarded as the founder of geology as a scientific discipline, particularly after the publication of De Natura Fossilium in 1546. Nicholas Steno contributed significantly to stratigraphy with the law of superposition, the principle of original horizontality, and the principle of lateral continuity. The term geology first appeared in writings by Ulisse Aldrovandi in 1603 and was further used by Jean-André Deluc in 1778, becoming a standard term introduced by Horace Benedict de Saussure in 1779. The word derives from the Greek terms meaning earth and speech. Another account attributes the term to Mikkel Pedersen Escholt, who used it in Geologia Norvegica in 1657. William Smith was instrumental in developing some of the first geological maps and ordered rock strata based on fossil content. In 1763, Mikhail Lomonosov published On the Strata of Earth, addressing the processes governing geological change in the Earth's historical narrative. James Hutton, often considered the first modern geologist, presented his theory of the Earth in 1785, arguing for an older Earth that allowed significant geological processes to occur over time. His ideas were expanded in a 2-volume work published in 1795. Hutton's followers, known as Plutonists, believed in volcanic origins for some rocks, contrasting with the Neptunists, led by Abraham Werner, who argued all rocks originated from a primordial ocean. In 1809, William McClure created the first geological map of the U.S., having surveyed nearly every state. His findings were shared with the American Philosophical Society, predating William Smith's map of England by 6 years while employing a different classification. Sir Charles Lyell published Principles of Geology in 1830, promoting uniformitarianism, the idea that slow geological processes are ongoing. This contrasted with catastrophism, the notion that Earth's features resulted from infrequent catastrophic events. Though Hutton had laid the groundwork for uniformitarianism, acceptance came slowly. Much of the 19th century focused on determining the Earth's age, with estimates ranging widely. By the early 20th century, radiometric dating placed the Earth's age at about 2 billion years, suggesting a vast time frame for geological processes. The 20th century saw significant advancements, particularly with the theory of plate tectonics emerging in the 1960s. This theory, which unified observations of seafloor spreading and continental drift, revolutionized Earth sciences. Today, the Earth is understood to be approximately 4.5 billion years old. The rock cycle is a fundamental concept in geology that explains the transitions among the 3 main rock types: sedimentary, metamorphic, and igneous. Each rock type undergoes changes when removed from its equilibrium conditions. For instance, an igneous rock like basalt may break down and dissolve when exposed to the atmosphere, or it may melt when subducted beneath a continent. The processes that drive the rock cycle, such as plate tectonics and the water cycle, ensure that rocks do not remain stable and instead change as they move through different environments. This cycle illustrates the relationships among the rock types and how they transform from one to another over time. Because of its cyclical nature, the rock cycle is considered both a geologic and a biogeochemical cycle on planets that support life. When rocks are pushed deep beneath the Earth's surface, they may melt into magma. If conditions change, causing the magma to solidify, it forms igneous rock. Magma that cools within the Earth is called intrusive or plutonic rock. It cools slowly, resulting in a coarse-grained texture, as seen in granite. When magma reaches the surface through volcanic activity, it becomes lava. Lava cools rapidly in the atmosphere, forming extrusive or volcanic rocks. These are typically fine-grained, and if cooled extremely fast, they may lack crystal formation, creating natural glass like obsidian. The most common fine-grained rock is basalt. All 3 main types of rocks, igneous, sedimentary, and metamorphic, can melt into magma and subsequently cool into igneous rocks. Secondary changes in rocks occur through epigenetic processes at low temperatures and pressures. These changes can be categorized under several headings, typically associated with specific groups of rocks or minerals. However, it is common for multiple alterations to take place within the same rock. Silicification involves the replacement of minerals with crystalline or cryptocrystalline silica, primarily in felsic rocks like rhyolite, but also in serpentine. Kaolinization refers to the decomposition of feldspars, the most prevalent minerals in igneous rocks, into kaolin along with quartz and other clay minerals, best illustrated by granites and syenites. Serpentinization is the transformation of olivine into serpentine, often accompanied by magnetite, and is typical of peridotites, although it can also occur in many mafic rocks. Urolitization involves the secondary formation of hornblende in place of augite. Chloritization describes the alteration of augite, biotite, or hornblende to chlorite, commonly observed in diabases, diorites, and greenstones. Finally, epidotization occurs when biotite, hornblende, augite, or plagioclase feldspar transforms into epidote. Rocks exposed to high temperatures and pressures can change physically or chemically to form metamorphic rock. Regional metamorphism occurs when large masses of rock are affected over a wide area, often linked to mountain-building events in orogenic belts. These rocks typically show distinct bands of different minerals and colors, a feature known as foliation. Another type of metamorphism is contact metamorphism, which happens when a body of rock comes into contact with an igneous intrusion. The heat from the magma alters and recrystallizes the surrounding country rock. This process can also involve the addition of fluids from the magma, introducing new chemicals to the rocks, known as metasomatism. Any existing type of rock can be transformed through metamorphic processes. Rocks exposed to the atmosphere experience instability and undergo weathering and erosion. These processes break the original rock into smaller fragments and transport dissolved materials. The accumulated material is buried by additional layers. While a single grain of sand retains its classification, a rock composed of fused grains is classified as sedimentary. Sedimentary rocks can form through various processes. Clastic sedimentary rock is produced from the lithification of smaller fragments. Biogenic sedimentary rock originates from the accumulation and lithification of material created by living organisms, such as fossils. Precipitate sedimentary rock forms when minerals precipitate from a solution due to evaporation. Clastic rocks can result from fragments of any larger rock type that have been broken apart by erosion, or from organic material, such as plant remains. In contrast, biogenic and precipitate rocks arise from the deposition of minerals dissolved from other rock types. Plate tectonics. In 1967, J. Tuzo Wilson published an article in Nature that described the repeated opening and closing of ocean basins, particularly in the Atlantic Ocean. This idea became known as the Wilson cycle, and it played a significant role in the plate tectonics revolution. The Wilson cycle has greatly influenced the contemporary understanding of the rock cycle, establishing plate tectonics as the driving force behind it. At mid-ocean divergent boundaries, new magma forms from mantle upwelling and a shallow melting zone. This basaltic magma represents an early phase in the igneous rock cycle. As tectonic plates on either side of the ridge move apart, the new rock is transported away from the ridge. Heated seawater circulating through fractures interacts with the rock, initiating retrograde metamorphism. Subduction zones are critical areas where new basaltic oceanic crust meets as it moves away from the spreading ridge. When this crust is pulled back into the mantle, the pressure and temperature increase, leading to a restructuring of the rock's mineralogy through a process called metamorphism, which forms eclogite. As the basaltic slab and some sediments descend, water and other volatile materials are expelled, rising into the overlying wedge of rock above the subduction zone, where pressures are lower. In this wedge, the combination of lower pressure and high temperature, along with the addition of volatiles, causes melting. The resulting buoyant magma rises through the overlying rock, leading to volcanism at island arcs or continental margins. The lavas produced are more silicic the further they are from the edge of the volcanic area, suggesting a deeper source and more differentiated magma. Sometimes, segments of the metamorphosed downgoing slab may be thrust up or abducted onto the continental margin. This results in blocks of mantle peridotite and metamorphic eclogites being exposed as ophiolite complexes. The volcanic material that erupts is often subject to rapid erosion, influenced by climate conditions. Sediments accumulate in the basins on either side of an island arc. As these sediments become more buried, lithification occurs, forming sedimentary rock. Continental collision occurs during the final phase of the Wilson cycle when two continental masses or smaller terrains converge at a specific zone. Since both consist of low-density silicic rock, neither can be subducted. The meeting of these continental crusts generates immense compressional forces that distort and reshape the rocks involved. This process leads to regional metamorphism within the resulting orogeny, or mountain-building event. The compression causes folding and faulting, forming a mountain range and affecting all pre-existing igneous, volcanic, sedimentary, and earlier metamorphic rock units, subjecting them to a new metamorphic event. Accelerated erosion occurs in high mountain ranges created by continental collisions. These mountains face immediate erosion, leading to the formation of large sediment piles in nearby ocean margins, shallow seas, and continental areas. As these sediment accumulations are buried deeper, they undergo lithification, transforming into sedimentary rock. The metamorphic, igneous, and sedimentary rocks of the mountains contribute to these sediment piles in the adjoining basins, eventually also becoming sedimentary rock. The plate tectonics rock cycle is an evolutionary process. Magma generation occurs in environments such as spreading ridges and above subduction zones. This process favors the eruption of silicic and volatile rich materials found in the crust and upper mantle. Lower density materials tend to remain within the crust rather than being subducted back into the mantle. As magma forms, the initial melt consists of silicic phases, which have a lower melting point. This results in partial melting and further segregation within the lithosphere. The buoyancy of silicic continental crust means it is generally not subducted. Over time, the continental masses grow larger. The presence of abundant water on Earth is crucial for the rock cycle. The most apparent role of water is in weathering and erosion. Water, including precipitation, acidic soil water, and groundwater, effectively dissolves minerals in rocks, particularly igneous, metamorphic, and marine sedimentary rocks that become unstable under surface and atmospheric conditions. It carries away dissolved ions and broken down fragments resulting from weathering. Running water transports significant amounts of sediment in rivers back to the ocean in inland basins, where accumulated and buried sediments transform back into rock. Water also plays a less visible role in metamorphism. In fresh seafloor volcanic rocks, seawater, sometimes heated, flows through fractures and crevices in the rock. This process, exemplified by serpentinization, significantly contributes to the alteration of volcanic rock. In addition, the role of water and other volatiles in the melting of existing crustal rock above a subduction zone is essential in the rock cycle. Water, along with carbon dioxide and other carbon compounds from marine limestone in the sediments above the descending slab, introduces melt-inducing volatiles. This interaction ties the carbon cycle into the overall rock cycle. Cyclic sediments are a type of layers found in sedimentary rocks. Migmatite is a mixture of metamorphic rock and igneous rock. Plate tectonics is the scientific theory that Earth's lithosphere is made up of several large tectonic plates that have been slowly moving for about 3 to 4 billion years. This theory builds on the earlier concept of continental drift, which emerged in the early 20th century and gained acceptance among geoscientists after the evidence for seafloor spreading was confirmed in the mid-1960s. The processes that generate these plates and shape the Earth's crust are collectively known as tectonics. The lithosphere, which includes the crust and upper mantle, is fractured into 7 or 8 major plates and many smaller ones. The interactions at plate boundaries where these plates meet determine their movement types: convergent, divergent, or transform. Typically, the relative movement of these plates is between 0 and 10 centimeters per year. Areas around faults are geologically active and often experience earthquakes, volcanic activity, mountain formation, and the creation of oceanic trenches. Tectonic plates consist of oceanic lithosphere, which is denser and thinner, and continental lithosphere, which is thicker and buoyant, with each topped by its respective crust. In convergent boundaries, one plate often subducts beneath another, descending into the mantle, which reduces the total area of Earth's surface. This loss is offset by the formation of new oceanic crust at divergent boundaries through seafloor spreading, maintaining a constant surface area in a tectonic cycle. Currently, Earth is the only planet recognized to have active plate tectonics. However, evidence points to tectonic activity on other celestial bodies. For instance, Europa, a moon of Jupiter, displays evidence of ice crustal plates that move similarly to Earth's tectonic plates. Mars and Venus are believed to have experienced tectonic activity in the past, although not in the same manner as Earth. Tectonic plates are relatively rigid and float atop the ductile layer known as the asthenosphere. Variations in density within the mantle create convection currents, which drive the slow motion of Earth's solid mantle. At a seafloor spreading ridge, plates diverge from each other, and as the newly formed crust moves away, it cools, increasing in density, which aids its motion. In contrast, at subduction zones, the colder, denser oceanic crust sinks into the mantle, forming a downward convecting limb of a mantle cell, which is a significant factor in driving plate movement. The roles of other proposed influences, such as convection, mantle upwelling, and tidal forces from the moon, remain topics of ongoing research and debate. The outer layers of Earth are divided into the lithosphere and asthenosphere. This division is based on differences in mechanical properties and heat transfer methods. The lithosphere is cooler and more rigid, while the asthenosphere is hotter and flows more easily. The lithosphere loses heat through conduction, while the asthenosphere transfers heat by convection and has a nearly adiabatic temperature gradient. This should not be confused with the chemical subdivision into the mantle and the crust. A piece of mantle may belong to either the lithosphere or asthenosphere, depending on its temperature and pressure. Plate tectonics hinges on the concept that the lithosphere exists as separate and distinct tectonic plates that move on the viscoelastic asthenosphere. These plates move at rates ranging from 10 to 40 millimeters per year at the mid-Atlantic ridge, similar to the growth rate of fingernails, to about 160 millimeters per year for the Nazca plate, about as fast as hair grows. Tectonic lithospheric plates consist of lithospheric mantle beneath one or two types of crustal material, oceanic crust and continental crust. Oceanic crust, formed at seafloor spreading centers, is denser than continental crust due to its composition of less silicon and more heavier elements. This density difference causes oceanic crust to mostly lie below sea level, while continental crust rises above it. Average oceanic lithosphere is generally about 100 kilometers thick. Its thickness varies with age. As it cools, it conducts heat from below and radiates it into space. Being formed at mid-ocean ridges, its thickness depends on the distance from these ridges. At mid-ocean ridges, it can be about 6 kilometers thick, increasing to more than 100 kilometers at subduction zones. The thickness of continental lithosphere typically measures around 200 kilometers, although this varies across different regions, such as basins, mountain ranges, and stable cratonic interiors. Plate boundaries are where two tectonic plates meet, leading to geological events like earthquakes and the formation of mountains, volcanoes, mid-ocean ridges, and oceanic trenches. Most of the world's active volcanoes occur along these boundaries, with the Pacific Plate's Ring of Fire being particularly notable. Some volcanoes are found within the plates themselves, often linked to internal plate deformation or mantle plumes. Tectonic plates can comprise either continental crust, oceanic crust, or both. For example, the African plate includes the continent as well as portions of the Atlantic and Indian Ocean floors. Certain oceanic crust sections, known as ophiolites, have been pushed upward instead of being subducted beneath continental crust at destructive plate boundaries, allowing these fragments to be preserved within the continental crust. 3 types of plate boundaries exist, characterized by the way the plates move relative to each other. These boundaries are associated with different surface phenomena. Divergent boundaries, also known as constructive or extensional boundaries, occur where two plates slide apart. In ocean-to-ocean rifting, these boundaries form through seafloor spreading, allowing for the creation of new ocean basins such as the Mid-Atlantic Ridge and East Pacific Rise. As the oceanic plate splits, a ridge develops at the spreading center, leading to an expansion of the ocean basin. This process can produce many small volcanoes and shallow earthquakes. In continent-to-continent rifting, divergent boundaries can also cause new ocean basins to form as continents split, such as in the East African Rift, Baikal Rift, West Antarctic Rift, and Rio Grande Rift. Convergent boundaries, or destructive boundaries, occur where two plates move toward each other. This can create a subduction zone, where one plate descends beneath the other, or lead to continental collisions. There are two types of subduction zones: ocean to continent and ocean to ocean. In ocean-to-continent subduction, the denser oceanic lithosphere sinks beneath the lighter continental crust. Conversely, in ocean-to-ocean subduction, older, cooler oceanic crust sinks beneath less dense oceanic crust. Deep marine trenches are usually associated with subduction zones, and the basins that form along the active boundary are called foreland basins. As the descending plate moves into the asthenosphere, a trench forms, and as it heats up, it releases water and other volatiles into the mantle. This addition lowers the melting point of the mantle material, resulting in magma that often leads to volcanism. Ocean-to-ocean subduction typically creates trenches in an arc shape, causing magma to rise and form curving chains of volcanic islands, like the Aleutian and Mariana Islands. In ocean-to-continent subduction, mountain ranges form, exemplified by the Andes and the Cascade Range. In continental collision zones, two masses of continental lithosphere converge, compressing and uplifting without subduction, forming mountain ranges such as the Himalayas and the Alps. The closure of ocean basins can occur in these boundaries. Transform boundaries, also referred to as conservative or strike-slip boundaries, are where plates slide past each other without being created or destroyed. Movement along these boundaries can be sinistral, with the left side moving toward the observer, or dextral, with the right side moving toward the observer. Transform faults often occur at spreading centers, where they can generate strong earthquakes. The San Andreas Fault in California is a well-known example of a dextral transform boundary. Other plate boundary zones exist where the interactions are less clear, often forming broad belts that display various types of movements over time. Tectonic plates move due to the relative density of oceanic lithosphere and the weakness of the asthenosphere. The heat dissipation from the mantle serves as the energy source that drives plate tectonics through processes such as convection and large-scale upwelling. A significant factor in plate motion is the excess density of oceanic lithosphere, which sinks in subduction zones. At mid-ocean ridges, new crust forms and is initially less dense than the underlying asthenosphere. Over time, as it cools conductively and thickens, the oceanic lithosphere becomes denser. This increased density allows it to sink into the deep mantle at subduction zones, generating much of the force needed for plate movement. The weakness of the asthenosphere enables tectonic plates to move smoothly toward these subduction zones. Driving forces related to mantle dynamics. For much of the first quarter of the 20th century, the leading theory explaining tectonic plate motions involved large-scale convection currents in the upper mantle, transmitted through the asthenosphere. This theory, developed by Arthur Holmes and others in the 1930s, was recognized as pivotal for the acceptance of Alfred Wegener's earlier ideas about continental movement. Despite its acceptance, it remained a topic of debate because the prevailing view still considered Earth to be static until major breakthroughs emerged in the early 60s. Advancements in 2- and 3-dimensional imaging of Earth's interior, known as seismic tomography, reveal a varying lateral density distribution throughout the mantle. These density variations arise from material differences in rock chemistry, differences in mineral structures, or thermal changes due to heat energy. The interaction of these varying densities leads to mantle convection driven by buoyancy forces. The relationship between mantle convection and plate motion is an ongoing area of study within geodynamics. A key aspect is the transfer of energy to the lithosphere, which is necessary for tectonic plate movement. Two main types of mechanisms are thought to influence plate motion: primary and secondary. Primary mechanisms involve large-scale convection cells, while secondary mechanisms emphasize the friction between the convection currents in the asthenosphere and the more rigid lithosphere above. The inflow of mantle material is particularly important in subduction zones at ocean trenches, where the downward pull on plates can create a process known as slab pull. This occurs when basal tractions act on the plate as it descends into the mantle, affecting both the upper and lower sides of the slab. Additionally, pieces of slabs that break off and sink can create viscous mantle forces that help drive plates through a process known as slab suction. In the theory of plume tectonics, developed by researchers in the 1990s, a modified concept of mantle convection currents is presented. This theory asserts that superplumes rise from the deeper mantle and act as drivers or substitutes for major convection cells. The origins of these ideas date back to the early 1930s, linked to the works of Belousov and Van Bemmelen, who initially opposed plate tectonics and positioned the mechanism within a fixed framework of vertical movements. Later, Van Bemmelen refined the concept with his undation models, suggesting that mantle blisters drive horizontal movements through gravitational forces acting away from regional crustal doming. Modern theories resonate with these concepts, proposing that hotspots or mantle plumes remain fixed while oceanic and continental lithosphere plates move over them, leaving traces in the geological record. However, these phenomena are not considered primary driving mechanisms. Instead, they are viewed as modulators of geological processes. This mechanism is still used to explain the breakup of supercontinents during certain geological epochs, and it has supporters among scientists studying Earth expansion. Thank you for learning and relaxing with me tonight. This is the end of the chapter on rock geology. Feel free to continue learning in the next chapter.